Myself, Dr. Tejashwini, Assistant Professor, Department of ETE in USNT. I'll be doing the lecture video series on signals and systems. And this is module 1, Introduction to Signals and Systems. And in this module, we'll be covering all these topics: definition of signals and systems, examples of communication and control systems, classification of signals, operation of signals, elementary signals. Along with that, there will be problems on classification of signals, operation of signals, and we will be seeing the problems in depth. So let us start with definition of signal. First, to say what is a signal. A signal is defined as a function of one or more variables that conveys information about some physical phenomena. When I say function, a signal can be represented using one variable or more than one variable, depending upon the type of variable used. If a function depends on a single variable, then such signals are called as one-dimensional signals. For example, speech signal, biosignals like ECG, EEG, acoustic waves, like that. All these are one-dimensional signals where a function depends only on one variable. Similarly, if a function depends on more than one variable, might be 2 variable, 3 variable, like that, more than one variable, such signals are called as multidimensional signals. One example is your image, where the image signal is represented as a function of brightness based on spatial variables x and y. So we'll be having 2D images there, and the image is called as two-dimensional signals. Like that, we can have signals is a function of one or more variables. So in general, we can say that a signal will convey some information. For example, if we are approaching a patient is approaching a doctor for his illness, how will the doctor know about the health condition of the patient? By checking his temperature, he will know whether the patient has fever or not. So what does the temperature value tells him? It gives him the information about the condition of the patient. So like that, in general, we can say that a signal conveys some information to others. So coming to the system, what do you mean by system? A system is formally defined as an entity that manipulates one or more signals, accomplishing a function, thereby yielding a output signal. Here, for the system, the input will be a signal. So the system performs some operation on the input signal and it will give some output signal. That output signal can be a new signal or the estimate of the input signal. So signals that are given as an input for the system, generally we refer it as input signal. And secondly, the signals that are produced by the system after performing some operation on the signal, such signals are called as output signals. And the system which produces the signals within the interconnection of systems, and such signals we refer it as internal signal. And the connection between the signal and system can be represented as shown in the block diagram. So here in the block diagram, we have a system which will perform some operations on the input signals. The input signal can be a single signal or m number of inputs can be given to the system. So the system will perform some operations on these input signals, thereby it manipulates these input signal and produces the output signal. And the signals which are produced inside the system, and such signals are referred as internal signals. For example, we can say an audio amplifier which consists of a microphone, an amplifier and a speaker. So this is one example where the acoustic signals are taken as an input from the microphone. It converts that into the electrical signal. Later on, these electrical signals are amplified by the amplifier, and At the end, the speaker will convert these amplified electrical signals back to the acoustic signal. So we can say here the input is an acoustic signal and the output of a system is also an amplified acoustic signal, and the operation which will involve in converting the acoustic signal to electrical signal and again amplifying, then converting back into the acoustic signal is done using microphone, amplifier and speaker. Now coming to next topic is the examples of communication control systems. So the first is communication systems. We know that the basic components of communication systems are transmitter, channel and receiver, and this is the block diagram of the communication system where the input will be a message signal, and this entire thing is your system which involves transmitter, channel and receiver. So the message signal is modulated or converted into digital. Generally the message will be in analogous in nature, and nowadays we have seen all the information is transmitted through digitally only. So the message signal is converted to analog signal and it is modulated, and the modulated signal is transmitted through the channel. So in the channel, due to the interference of noise and any other parameters, the signal can be distorted, and at the receiver end the signal has to be regenerated, then demodulated, then converted back to the analog signal. So we'll be getting an estimate of the message signal there. This is the block diagram of a communication system, and the components like whatever we have, the elements, three basic elements, transmitter, channel and receiver, all these things forms the system, and the input is the message signal and the output is the estimate of the message signal, and all these intermediate signals like whatever I get, that is the output of the transmitter, output of the channel, and all those are internal signals. Coming to the next one, let us see some of the examples of control systems. When we talk about the control system, so the control systems has both closed loop system and even the open loop system. It is an interconnection of subsystems which will perform some operation on the input signal, thereby we get some output signal. And let us see what is a closed loop system. In this closed loop system, the control action is somehow dependent only on the closed loop system. The control action is somehow dependent on the output system, that is we have a feedback from the output system, and this is the block diagram of the closed loop system where we have a reference transducer. The input is converted to the electrical signal, required electrical form. Then we have a controller and a plant where like during the plant we can have even the disturbance there, and the output of the plant is given as a feedback to the like input here. So the reference output of the transducer and the feedback element is being used, and based on the error here the system is controlled. That is what your closed loop control system is. One of the examples of closed loop control system is your automatic electric irons, where the iron box starts to heat up. So like once the threshold heat is generated by the iron box, it stops automatically. So after a few seconds or minutes, again the iron box starts heating. That is the feedback loop, and based on that the automatic electric iron boxes works. Similarly, voltage stabilizer also. These are some of the examples of closed loop systems. And coming to the open loop system, we will see the control systems. One example is the open loop systems, where in this open loop the control action is totally independent of the output of a system. So this is the block diagram of the open loop system where we have a controller and a plant, and the control output is independent on the output system. This controller is independent on the control output, so there is no feedback in this case. Such a control system is called as your open loop control systems. One such examples for this is your automatic washing machine, where for the washing machine we have more than one inputs, dirt clothes, along with that we use washing powder, then comfort, like that more than one inputs will be given for the washing machine. And like what will the machine does, like it takes all these inputs, it cleans the dirty clothes, like it washes completely, it rinses, then it even dries and the output will be cleaned, dried clothes. So like in advanced machine, like dried clothes also will be getting. That is your automatic washing machine. So where the output is not dependent or the controller is not dependent on the output there. Similarly, we have even electric hand dryer also, where the dryer will dry the hair. So even that controller does not depends upon the output of the system. So this is your open loop systems. These are some of the examples. So coming to the classification of signals, the third topic in that. So we have 6 types of classifications. The first one is continuous time signals. We can even call it as CTS. Discrete time signals, it is DTS. And the second one is analog signals and digital signals. And third one is even signal and odd signal. Fourth one is periodic signals and non-periodic or aperiodic, any one can be used signals, and random signals and deterministic signals, and the last one is power signals and energy signals. So today's section we'll be seeing the continuous time signals, discrete time signals, analog signals and digital signals, and even and odd signals. So let us start with continuous time signals and discrete time signals. So it is CTS and DTS. We will see how to define a signal based on how a signal is defined as a function of time. We can classify it into CTS or DTS. That's your continuous time and discrete time. The name only specifies the continuous time means the signal is defined continuously for all the values of time. So a signal x of t, generally we have a notation for the continuous time signal as x of t here. So a signal x of t is said to be continuous if it is defined for all the values of t, and one such example is this continuous time signal. It can be defined for continuous throughout the time interval. And generally your continuous time signal is a natural occurring signals, where a physical waveform such as your acoustic wave, light wave is converted to electrical signals. So in real time, like whatever signal we get is continuous in nature. And how to represent these continuous time signals, we have these 2 methods of representing. The first method is formula method, where we can mathematically express the signal in terms of some mathematical equations. One such example is given as x of t is equal to e to the power minus t, where we get an exponential signal. One more is your sinusoidal signal, x of t is equal to sin t. Like that we can represent the continuous time signals like using some formula based method. The second one is graphical method, where we can represent like using the waveforms like this. And now the second type is discrete time sequences, and this discrete time sequences is often derived from the continuous time sequences. How we do it is by sampling the signal at like equal intervals of time. So to do that we require sampling frequency. So let capital T denotes the sampling period and n denotes an integer. It can be plus or minus, negative values and positive values. So generally like what we do is the continuous time signal is sampled at equal intervals of time. That is, we are going to sample this signal, cut into pieces like this at equal intervals of instant, like t is equal to nt. This will yield a sample values, the previous signal like whatever we have got, like when we cut into pieces like at like equal intervals of time, we will get samples like this. Each one is a sample there. And this is represented by x of n. Generally x of nt can also be written as x of n, where n is equal to 0, plus or minus 1, plus or minus 2, plus or minus 3. Like what does this imply? At 0, I have a signal of amplitude minus 1. At minus 1, I have a signal of amplitude minus 2. At minus 2, time t is equal to minus 2, one signal of amplitude 2. Here, generally like so, like what we do is for discrete time, we like represent using x of n, and your time axis is represented so like in terms of n instead of t there. So please like remember these two. Your continuous time signal we represent using x of t, and your time axis is indicated by t. At t is equal to minus 3, minus 2, minus 1, like that. And similarly, your discrete time sequences, it is of the form x of n, and the time is represented with respect to n value. At n is equal to -3, I have a signal of amplitude -1. So this amplitude is called as x of -3, and this is x of -2, x of -1, x of 0, x of 1, x of 2, x of 3. I can represent the sequence like this also. That is your discrete time sequences. We can represent by sequence form also, where this x of -2, x of -1, all these indicates the amplitude at n is equal to -2, n is equal to -1, n is equal to 0, n is equal to 1 represent respectively. So how to represent this discrete time sequences? We have three methods. The first method is formula method. That is, we can represent the signal using some equations, mathematical equations. X of n will be x of n plus 1, x of n is equal to n, like that some formula based can be used. The second method is graphical method, where I can use some waveforms to represent the signal. And the third method is sequence method, where only the amplitudes of the signal can be represented. And like if there is nothing specified here, the first sequence indicates your origin. So generally the origin can be indicated using, so when we use an arrow like this, that indicates the origin. Then next comes analog signal and digital signal. So it is a subsection, or I can say sub-classification of continuous time and discrete time. So what do you mean by analog signal? So like in continuous time signal, the signal is defined for entire duration of time, -infinity to +infinity. Whereas in analog signal, same continuous time signal x of t, when we are representing between some interval, comma, say a comma b, here a can be -infinity, b can be +infinity, or a can be -5, b can be +5, between some interval of time, then such signals are called as analog signals. So only we say it as sub classifier of CTS, that's your continuous time signal. So continuous time signal is represented for the entire duration of time, but when we have an interval of time, then we call it as analog signal. Similarly, discrete sequences also, we have a finite number of distinct values, that is your signal is specified for a finite duration of time, -n to +n. That is what your analog and digital signal is. The next type of signal is your even signal and odd signal. So here the condition will be defining both for continuous time and discrete time. A continuous time x of t always we specify as continuous time signal. So a continuous time signal is said to be even if it satisfies the following condition. Like what is that condition? X of -t should be equal to x of t for all the values of n. See, one small example I have taken here, where the signal is varying from -3 to +3, and I have a waveform like this. See, like if I fold at the origin and fold on both the sides, the signal will be same. It is symmetric at the origin. See, at 0 if I fold, the signal is same. Okay, and such signals are called as continuous time signals. So like even signals, that is x of -t will be x of t. And similarly, discrete time sequence also, when x of n is said to be even if the following condition is satisfied. What is the following condition? The following condition is x of -n should be equal to x of n for all the values of n. So what does this mean? See, at n is equal to 1 and at n is equal to -1, I have a same signal of amplitude 2. That is x of -1 is equal to x of +1. So x of -2, I have a sample of amplitude 2. Again at 2 also I have a sample of amplitude 2. So these two signals are same. So x of -3 and x of 3 is same. So when such condition is satisfied, and all these signals are called as even signals. And like seeing at these two waveforms, like we can conclude that the signal is, so all like even signals are symmetric with respect to the origin. Like what do you mean by this? So like if I fold at the origin and it is same on both the sides, that is symmetric about the origin. Coming to the odd signal, So when is a continuous time signal said to be odd? So like if it follows the following condition, that is x of minus t should be minus x of t for all the values of t. Similarly, a discrete time sequence also, it is said to be odd like if the following condition is satisfied, x of minus n should be minus x of n for all the values of n. We can see here, see at 1 I have a signal of amplitude 1 here, whereas at minus 1 signal of amplitude minus 1. And if you see between 2 and 3 I have a waveform like this, whereas between minus 3 and minus 2 a waveform just opposite to this here. So it is antisymmetric. Similarly, see here for discrete time sequences, at 1 I have a signal of amplitude 1, but at minus 1 signal of amplitude minus 1. So x of minus n is equal to minus x of n. So when I see these two waveforms, we can say that the odd signal is antisymmetric about the origin. Okay, next we will see random signals and deterministic signals. What do you mean by random signals? Random signals means the occurrence of such signals are unknown to us, and we cannot represent such signals like in terms of some mathematical expressions or equations. For example, noise. We don't know at like what time the noise will occur and like how we can express the noise. So such signals are called as your random signals, whereas a deterministic signal means a signal which we can represent or determine using some mathematical equation, and the occurrence of such signal is known to us.